Today we're going to learn some coordinate systems in 3 dimensions. The purpose of these is much like polar coordinates in 2 dimensions. Sometimes there's a nice symmetry that allows different coordinates to make your calculus easier. So there's actually no calculus today. We're just going to learn some coordinate systems that are used in lots of applications. And then the calculus comes later, and you'll see when you have a convenient coordinate system, the integrations, the derivatives, those kind of things are a lot easier. Here's what we did in 2 dimensions, right? In 2 dimensions, we said, well, if you have a radial symmetry, like maybe there's a planet going around in a circular orbit or something, or just the gravitational force itself has radial symmetry, then it's more convenient to write, instead of dropping a perpendicular and say this point on the x-axis is x, and drop a perpendicular in here and say the point on the y-axis is y, and describing it with an ordered pair x, y. We could instead take the radial distance from the origin but to the point, call that r, call this angle counterclockwise from the x-axis theta, and describe it by an ordered pair r theta. Just like each xy identified a unique point, each r theta identified a unique point. We also did one more thing for convenience in applications. We allowed to also go to the opposite direction of the point and go and take r to be negative and back up to the point. So then r and theta could be any ordered pair. There was a drawback. You didn't get a unique ordered pair this way. xy, each point has a unique xy by dropping this 2 perpendicular, but here I can add any multiple of 2 pi to theta and I get the same point, right? So there's an ambiguity. You could always add any integer multiple of 2 pi to theta, and that identified the same point. But each ordered pair, r theta, identified 1 point, and that was the important thing. Also, the origin, you could let theta be anything as long as r was 0, so that was an ambiguity. We're going to run into a similar kind of situation here. It's real convenient to take advantage of any sort of radial symmetry, but we're going to also wind up identifying a point with more than 1 coordinates. Here's an easy way to do it. If I have a point in 3 space, x, y, z space, I could drop z. I could take my z coordinate to be the height above the xy plane, or it could be negative if I'm down below. And then take that point of projection down the xy plane, take its distance from the origin, call it r, the angle counterclockwise in the xy plane, theta, and what we've got is polar coordinates, r, theta, add z, the position up or down to the point vertically. So it's really polar coordinates, add z, except in most books, you add a restriction, and it's true in your book, that r can't be negative. So it's polar coordinates, add z, except r can't be negative, is used to identify cylindrical coordinates. The technical reason for that is there's some problems with integration later if you allow r to be negative in 3 dimensions. Some books will allow, you'll see that in one of these things I do today, but it will restrict r to be non-negative. That's cylindrical coordinates. What are the equations for cylindrical coordinates? Well, it's polar coordinates, so x must be r cosine theta, y must be r sine theta, and z is z, since we just added z. Polar coordinates add z. And to go the other way, it's the same thing too. So if we put before r squared equals x squared plus y squared, since r is non-negative, we'll say r is actually the square root of x squared plus y squared. Tangent theta is y over x, and you have to pick the correct quadrant that the projection point falls into. Sometimes you have to add pi. Remember, in polar coordinates, if you're in quadrants 1 or 4, you just took the arc tangent of y over x and you got theta. But if you're in quadrants 2 or 3, you took the arc tangent plus pi, gave you a choice for theta. And then you could add a 2k pi to that, and that was also an allowed choice. Same thing here. You take the arc tangent if you're in quadrants 2 or 3. To get theta, you take the arc tangent plus in quadrants 1 or 4. You take the arc tangent plus pi in quadrants 2 or 3 to get the correct angle. Then you can add any 2k pi. So there's the same ambiguity. And now any point on the z-axis, you can let theta be arbitrary. And that'll identify the same point. Alright, so the same conversion equations from rectangular coordinates and polar, except you don't allow r to be negative, and then you add z. Here's another coordinate system that's useful. Suppose I take in any point in the plane, and I take its distance to the origin directly instead of taking the projection and then the distance. I'll call that distance rho, and then what does rho come out to be? Well, the rho is the distance from the origin then square root of x squared plus y squared plus z squared. So that's how we identify rho. And then when we drop this perpendicular, well, if this is phi, this alternate interior angle here, this is parallel to the z-axis, must also be phi. And remember from trigonometry, just like over here in polar coordinates, if this is the hypotenuse, this side is the hypotenuse cosine theta, so that this over this is cosine. And this is the hypotenuse times sine theta, so that this over this is sine. Similarly here, this must be rho cosine phi, and this side must be rho sine phi. So you see the r coordinate from cylindrical coordinates is directly rho sine phi. And the z coordinate is, rho cosine phi. I wrote the wrong thing there. Rho cosine phi. And then how do I find x and y? Well, if this is rho sine phi here, we know that this side, if we put theta in here, is the hypotenuse times the sine of theta, this angle. So it's hypotenuse rho sine phi sine theta. This side is the hypotenuse rho sine phi times the cosine of the angle theta, right? Looking at this triangle. So it's hypotenuse cosine theta makes it rho cosine theta sine phi. So here's the spherical coordinate transformations. X is rho cosine phi sine, rho cosine theta sine phi, y is rho sine theta sine phi, and z is rho cosine phi. Now we can go the other way. We do make a restriction on these. We again restrict all rho greater than or equal to 0. It's supposed to be the actual distance, and that's reflected in this equation transformation here. We also restrict phi to be between 0 and pi, or we can run into certain restrictions. So it says between here and here. And I'll give you a warning on these coordinates. In physics books, they often call this one theta and this one phi, so don't get mixed up. And in geodesy, when they're doing like latitudes and longitudes on Earth, or astrophysics where you're taking the right ascension and azimuth kind of thing, a lot of times they'll instead of measuring phi down from the z-axis, they'll measure it up from the xy plane because they want to make it a latitude. So be aware of those conventions. They're different in some engineering and physics courses and so forth. And sometimes in engineering books, instead of calling this rho, they'll call it r is another thing they like to do. They use rho for other purposes. So this is the math standard. This is what's in your book. And now theta is the same theta in spherical coordinates as you had in cylindrical coordinates, as you had in polar coordinates with R non-negative. So it has the equation tangent theta equals y over x. Phi, well, since we look here and rho cosine phi is the z coordinate, we just take the inverse cosine, and phi is the inverse cosine of z over rho, right? Just out of this, solving for phi. Divide by rho and take our cosine. Wait a minute, do we have the right quadrant? Do we have to worry about quadrant? We don't have to worry about it. This one always works. This one you have to pick the right, you have to add pi sometimes depending on the quadrant, but phi equals arc cosine z over rho always works because you want the unique angle between 0 and pi, and that's what the arc cosine gives you. So there's an introduction to these things. I think a really nice reference to this is to look online at LibreText, which is trying to make free textbooks for all sorts of courses, and they have a very nice presentation of these coordinate systems. Oh, it timed out on me again, of course. Sometimes you talk too long. And things go away. All right, here's their presentation of the topic, and it's pretty much our presentation here. Cylindrical coordinates, you take the point projecting out of the z-axis, you call it distance of the projection from the origin r, and then x and y, and then theta is the angle counterclockwise in the xy plane from the positive x-axis, and c is the z-coordinate transformed over. An important point is that just like when you put x, y, or z equals constant, you get interesting things, like you get a plane here, here's x equals 0, here's the y equals 0, here's the z equals 2 plane. You get planes parallel to one of the coordinate planes when you take x or y or z equals a constant. What do you get if you take a cylindrical coordinate equal a constant? Well, if you put r equal a constant, then you're taking all points that in the xy plane are at a distance r from the origin, that's a circle. And then z is arbitrary, right? If you just make the equation, r equals, suppose this is my equation in cylindrical coordinates now. I can get rid of the polar coordinates. What does the graph of r equals 2 look like? Well, it's equivalently, from polar coordinates, all points at a distance 2 from the origin. Oops, put it this way. And then z is arbitrary, so it looks like this. You can convert it to rectangular coordinates and also see it. It's a right circular cylinder of radius 2. The other way to do it is say, oh, this is square root x squared plus y squared equals 2, and you square both sides and get x squared plus y squared equals 2 squared, and recognize, oh yeah, that was a right circular cylinder rectangular coordinate. So you can either figure it by what the coordinate means, or you can convert it to rectangular coordinates. And that's true in a lot of these cases here. But the point is, if you put r equal a constant, you get a right circular cylinder. If you put theta equals a constant, then you can go in this direction. Z can be arbitrary, and you can go arbitrarily far out with r, and so you get a half plane bounded on the edge by the z-axis. And then you can figure this equation in rectangular coordinates to get it also. If you have theta equals, let's say, pi over 6, what does that convert to? I just take the tangent of theta equals tangent of pi over 6, which tangent is sine over cosine is 1/2 over square root 3 over 2 is 1 over square root 3. And now that's supposed to be y over x. And so if you have y over x equals 1 over square root 3, you have y equals 1 over square root 3x. It's a line from the origin, except one thing. What did I leave out here? Well, you have to keep track of the quadrant. This is only in the first quadrant in the xy plane. So it's actually restricted to x and y in the first quadrant. Let's just say x greater than or equal to 0 fixes that. So it's the ray in the xy plane, y equals 1 over square root 3x. Z arbitrary makes it a half plane. You can sketch it like that. Y equals 1 over square root 3x looks like that. And then you extrude it. So you can do it in the rectangular coordinates. It's easier just to draw this angle theta equals pi over 6, and then just go up and down. That's easier. But there's how you can sketch theta equals a constant. It's a half plane always. And then z equals a constant is a horizontal plane because it's the same z that you had in rectangular coordinates. Now you want to be able to convert these things. You just use those equations directly to what you had here. Polar coordinates, x equals r cosine theta. By the way, this is always r followed by theta followed by z. That's the order. So you see these cylindrical coordinates. You just say r cosine theta. It's like polar coordinates, 4 cosine 2 pi over 3. It comes out to be minus 2 using your trigonometry. Y is r sine theta is like polar coordinates. It's 4 sine 2 pi over 3 is 2 square root 3. And z is just carries over to negative 2. So here are the cylindrical coordinates for this point. Oops, not there. Somewhere here. Minus 2, 2 square root 3, and minus 2. There are the cylindrical coordinates. You can also draw these. The way to draw these is to turn the angle theta first. So you draw it to 2 pi over 3 here. And then you go out r is 4 units. And then you go up or down by the z amount. Negative 2, we go down 2. So turn, go out, and go down is an easy way to draw cylindrical coordinates when you want to sketch them. Well, how about this one? Suppose I have rectangular coordinates, 1, minus 3, 5. I wonder what the cylindrical coordinates are. Well, you think r is equal to, we're not going to put the plus or minus. This presentation allows r to be negative in cylindrical coordinates. It's unusual, I think. R is the square root x squared plus y squared is square root 10. So that's how far you are out from the origin. And that's what they pick at this step. They say we can pick either. And then theta, how do you get theta? Same thing as a polar coordinates. Tangent theta is y over x is minus 3 over 1 from the given coordinates. So we take theta is the arctangent negative 3 or arctangent plus pi. What do we do? X is positive, y is negative. The projection of this point is in quadrant 2, x positive, y negative. So we have to add pi. This should say arc tangent negative 3 plus pi is 5.03 radians. Right? This is, arc tangent is always an angle between plus and minus pi over 2. This is bigger than that. Alright, so there you get arc tangent plus pi. And then z just carries over as phi. So there's how to get these. It's just plug and chug. Just plug in polar coordinates and add z when you want to go from cylindrical to rectangular. It's just plug and chug, except you sometimes have to add pi to the arc tangent to go from rectangular to cylindrical. They aren't too bad, right? Here's some things we want to sketch. Sketch theta equals pi over 4. Just turn to pi over 4, draw a half plane. R squared plus c squared equals 9. A lot of these are easier if you convert them to rectangular. Just remember, r squared is x squared plus y squared, so this is x squared plus y squared plus z squared equals 9. Oh, it's a sphere of radius 3. Here it is down below. So r squared plus c squared becomes x squared plus y squared plus z squared equals 9, and there's the sphere of radius 3 at the origin. That's what it said. Suppose I have a surface z equals r. I wonder what that looks like. Well, we can write this equation. I think it's down here somewhere. Let's see. I guess they didn't do it. I'll do it on here. So one thing is converting points between the two coordinate systems. Another one is sketching equations and converting equations to do it. So suppose I have this one. Sketch v equals r and find its equation in rectangular coordinates to do it. Cartesian coordinates are sometimes called after Descartes, a philosopher, mathematician. If I have z equals r, or any multiple of r, it's going to come out to be the same thing. It's going to be a cone, and here's why. I rewrite this equivalently as z equals square root x squared plus y squared. And now z, we said, it is the same. Now we can square both sides and say equivalently this is z squared equals x squared plus y squared. And this, you recall, is a cone. Think of this as x squared over 1 squared plus y squared over 1 squared. From our section on quadratic surfaces, z squared equals x squared over a squared plus y squared over z squared is an elliptic cone with axes a and b here, but if they're the same, it's actually a circular cone. So this is a circular cone, and you can sketch this using the techniques we discussed last section. It's an hourglass, except I've left one thing off. What is it? When I square both sides, this is an equivalent to this. Here z had to be non-negative, because this means the non-negative of it has a square. And this allows z to be negative, so we have to add the restriction to make these equivalent. That z squared equals x squared plus y squared together with z greater or equal to 0 is equivalent. So it's the half cone. So it's a half circular cone. We can sketch it like this. And this goes up, no, it's not this one, goes up to infinity. Alright, so there's converting an equation. I have another example for you. Suppose I wanted to sketch r equals cosine theta. How do I sketch that one? Well, remember our conversion equations, what we have is not cosine theta or sine theta, but r cosine theta, r sine theta. So we try and get these things that we have here in order to convert them. So I'll multiply both sides by r and get r squared equals r cosine theta. And now I have almost an equivalent equation. You have to worry when you multiply both sides by r, I just introduced some new solutions, right? R equals 0 is a solution here. We mentioned this in polar coordinates before. For any angle theta, it wasn't before. Here, maybe the origin wasn't a solution, right, in polar coordinates thinking. So you have to check. Well, when theta equals pi over 2, r could be 0, made the origin a solution already. So even though I have some new solution pairs r theta, here theta could be pi over 6 and r could be 0 and would satisfy it, but not here. I introduced some new pair of solution r theta, but I introduced no points in 3 space, right? The origin is a solution here. The origin was already a solution. No new points, so I'll say these are actually equivalent. I can multiply both sides by r since the origin was already a solution. I don't have to throw it out now. Now, how do I do this? Well, this is x squared plus y squared equals r cosine theta is x. So you multiply through by r and make this something you recognize in a conversion equation. Now you can complete the square. X squared minus x plus y squared equals 0. Add 1/4 to each side. X squared minus x plus 1/4 plus y squared equals 1/4. That makes this a perfect square, right? I take 1/2 of this coefficient here, negative 1/2, and square it, and that gives me 1/4 here. So 1/2 of negative 1 squared is 1/4. That's what I need to add to make the perfect square. So I have x minus 1/2 squared plus y squared equals 1/2 squared. I recognize now the equation for a circle in the xy plane, and z is arbitrary. So if it's a circle on the xy plane and z is arbitrary, what we have is a cylinder here, centered at x equals 1/2. 1/2 out of here is 1/2, 0, 0 is the center of the circle on the xy plane, and radius 1/2, so it goes back to the origin. Here's the circle on the xy plane, and then I extrude it up and down forever, and I have a right circular cylinder is what this was. So sometimes you need to try and square both sides or multiply both sides by r to make this thing give you an equation you recognize in rectangular coordinates. One thing I wanted to point out is that even though you can convert all these from rectangular to cylindrical circles just by plugging in z equals whatever it is, x equals whatever it is, y equals whatever it is from the equations, sometimes it's easier to use other equations. Like here, if I want to convert to cylindrical, z stays as z. I can replace this with r cosine theta and this with r sine theta, and it works, but there's a bunch of simplification. Easier if I recognize somewhere in the equation an x squared plus y squared, I can replace that directly with r squared, and it's easier than plugging in r cosine theta and r sine theta. So this is the equation z equals square root 3r squared, which, since r is non-negative in cylindrical coordinates, this is z equals square root 3r is the equation in cylindrical coordinates. Now can I convert that to spherical coordinates? Well, I can replace, remember the coordinate transformation, r with rho sine phi and z with rho cosine phi. So this becomes equivalently in spherical coordinates, rho cosine phi equals square root 3 rho sine phi. Now, divide through by rho. When you do, you throw out the origin. The origin is a solution here. Is it still a solution? Well, you can get the origin still by taking phi equal pi over 4 to make these equal, and then rho equals 0 is still a solution. So the origin will still be a solution if I divide through by rho. And I have cosine phi equals sine phi, or if you like, tangent phi equals 1. That tells me phi must be pi over 4. This is the half cone that looks like this. If you recognize it, you can actually recognize it by squaring both sides here also. But it's got this equation in spherical coordinates, and this equation in cylindrical coordinates. You can also sketch it from here. A way to sketch it from here is to say, well, if I go out a distance r equals 1, then I go up a distance z equals square root 3, and this is a ratio constant of square root 3 to 1 for r and z, and so any distance out r out, if I go out 2, I go up 2 square root 3, I get this ray, and then theta is arbitrary, so I swing it around, and you can generate the cone by saying, oh, this is the relationship between r and z, and then let theta be arbitrary, revolves it around. So you can get the half cone from here, you can get the half cone from here, or you can square both sides of this equation and recognize it from the quadratic surfaces. Well, how about this one? Z minus x squared equals y squared. Once again, if you rewrite this by adding x squared to both sides, rather than substituting r cosine theta and r sine theta, it's easier to write c equals x squared plus y squared. Oh, that's just r squared. Maybe you recognize already this is a circular paraboloid. Elliptic paraboloid, the special case where it degenerates to a circle. But z equals r squared is then the equation in cylindrical coordinates. Right? Now, can I write that in spherical coordinates? Well, r is rho sine phi, so this is rho squared sine squared phi. Oops. And then z can be replaced with rho cosine phi, just by the direct substitution. Now, divide this through by rho, making sure you don't throw out the origin. The origin will still be a solution, so we'll say this is cosine phi equals rho sine squared phi. Sometimes people like to write this with rho a function of phi and theta, so you might write this as rho equals cosine phi over sine squared phi, and if I write sine squared phi as 1 over sine phi, 1 over sine phi, I recognize this as rho equals cotangent phi cosecant phi. Is a nice way to write this in spherical coordinates. Well, how about this last one? X squared equals 16 minus z squared. Sometimes you just don't see an obvious thing like r squared sitting in there. So you just convert it directly. X is r cosine theta, so this is r squared cosine squared theta equals 16 minus z squared. And there is an equation in cylindrical coordinates. If I see something to simplify, great. If I don't, then I just